welcome back to Project Helios. Today I'm going to be talking about Gefyra, which was the concept rocket we designed in the last video. So now we've actually made the rocket in CAD for you to see. I'm going to explain it from the front to the back, but this is the first iteration, so you may see some changes later on, but I'll try to explain any changes we do make. So to start off with the nose cone, we are going to be making our nose cone on a 3D printer using a material called PLA. PLA is quite impact resistant and it's really light compared to other materials we could use in this scenario. However, there is one big issue. The nose cone we have designed for this rocket is 40 centimeters long. Sounds okay, but our printer we use can only build nose cones 30 centimeters tall because of its build restriction. So we have 10 centimeters of nose cone which we can't print. However, we're going to counter that by making the nose cone in two separate parts. So we're going to have the first part, the lower part, and the second part, the upper part. So then we'll combine those two pieces together and end up with a nice, strong nose cone. We will do stress tests just to make sure that the two parts don't separate during flight. The second option we do have is we could get it industrially printed. They're pretty cheap for what they are, but it's still an extra cost, and when we can do it from home, it would just be way easier to do it ourselves. Okay, moving on to our next topic, recovery. So, Gefyra is going to have a design of recovery which most rockets don't use, so it's going to be separating from the middle of the rocket at apogee. So, there's going to be no drogue chute, it's going to separate into two segments. Hopefully we'll have enough drag to not go too fast during descent. It's going to lie flat during descent, and as it comes down we're going to deploy a main parachute closer to the ground, and the reason for this non-conventional design is because we need to prevent it from landing outside of the small area in the UK which we have to launch it. Currently we're still working on the mid-separation mechanism and how that's going to work. We have to do some testing and figure out calculations and other things just to make sure it's safe to do and that we will be able to do it without damaging the rocket or losing our rocket, which would be the worst case scenario. So I will explain the main parachute instead. We have made main parachutes for all of our rockets. All of the parachutes we've used so far in our project have been made by ourselves because it's pretty cheap to buy ripstop nylon online. However, for this project, because it's going to be moving down at a pretty fast speed, faster than what a conventional drogue parachute would let it come down at, we're going to have to be extremely careful so that we don't tear the parachute. So our first thought was we could buy a industrial parachute, well not really industrial, commercial parachute. So a commercial parachute would be much stronger than what we can make because they've tested it and they've had several iterations of it, and probably we could make something stronger, but our first option is to use a commercial parachute because we won't probably be ripping that anytime soon. It is quite disappointing that we have to use a commercial parachute, but what we will do on the side is we will be testing our own parachute under stress, simulations, calculations, and if the parachute manages to survive all of that, and we think it will be suitable for the rocket at that stage, we will actually try to put it in Gefyra instead of using a commercial parachute, which would be not ideal. The next topic is our avionics on the rocket. So the rocket will be using custom and commercial avionics because in the UK you are not actually allowed to use a custom flight computer unless it has been tested by the UKRA safety and technical community, and it has to be approved by them first. So for the most part, you can just say you're not going to be using your own flight computer. So what we're doing is we're planning on using Altus Metrum's flight computers because we've used them previously and they've worked really well for us. So we're still deciding on which exact computer we'll be using because we have cheaper and more expensive options, which we'll have to decide once we have the correct means to. But currently, we're looking at using a redundant main system, which means there are two ejection charges for the main parachute, and both those ejection charges will be firing near each other. But what happens is that sometimes after firing the first main ejection charge, your rocket can get stuck and actually knock them out of the rocket. But for that scenario, we have a few seconds later the second ejection charge, which will push it out just in case if it hasn't been able to. which means that your rocket's been saved, sort of, because if you would have not had the second ejection charge, your parachute would have not come out, and your rocket would have crashed, really. You would have never recovered it. So that's avionics over with. Next, I'm going to be moving on to the tubes we're using for the rocket. So for the tubes, we're using polycarbonate. And you may think, why polycarbonate? But the answer here for us is actually quite simple, because polycarbonate is light. It only weighs about 1.2 grams per centimeter cubed, compared to like carbon fiber, which may weigh up to 1.8. And it's also much cheaper, which in our scenario is a very big upside when you're trying to keep costs low. Which is why, for us, the option to choose polycarbonate tubes is quite straightforward. And moving on to our next topic, propulsion. So, for this rocket, we're going to be using Cicerone engines, which are made in America and are shipped to the UK. And they're actually quite hard to get a hold of at the moment because Cicerone is focusing on making munitions. So their hobby motors, which we're using, because they're not military grade at all. So the hobby motors that we buy off them are actually quite in shortage right now. But we've managed to find some, so hopefully it should be okay. So the engine we are using is a Cicerone, and in the picture you can see one of their engines. So as you can see, it's got 5 little grains. The grains are what we use to measure propellant. So there's 5 grains of propellant, which seems quite strong. It seems like quite a lot of force, right? But no, we're actually using a 6th grain and a 7th, which are called 6XL. So the 6XL is a really big engine, and we're using, if you want to see the exact engine, you can search up K300. It's a long burn engine, and it's really powerful for what the rocket we're using. So you can also see on the side of the engine there are 2 little canister looking tubes. So you may wonder, what are those? So imagine this: if you put an engine inside of a rocket tube that's bigger than the engine's loose, it can move left, it can move right, it can tilt tiny bit, and even if it tilts just by like 3 or 4 degrees in this rocket, your rocket will be moving in a direction you don't want it to be moving. It's going to not be able to fly straight because the thrust will not be moving straight down. So that's why we use centering rings. And centering rings, as you can see above, are these little, in this case, wooden rings, but we're going to be 3D printing them because it's simple for us and we got accessibility to a 3D printer in our lab. So these rings hold the engine, and they make sure that the engine is pointed directly down so that the rocket has the straightest flight path we can. And to just give a little demonstration on what a rocket would be without these centering rings, or a misaligned centering ring. If centering ring is even loose, it's going to be tilting it slightly, the engine, which is not going to be good for you. So imagine you are trying, the green line here is the ideal rocket path. You're going towards your goal, you get to the apogee above your goal, your rocket comes back down, and it lands within your recovery zone. So it's not drifted too far away. You're able to get it back easily. But the red line here is what a rocket could be if the thrust is not straight down. If the rocket is not flying in a straight line, it may begin to spin. It may begin to turn and fly in a different direction. And because of this, you don't fly as high because you're spending more energy to go in the wrong direction than you are going up. So you're going to end up having a rocket fly really far away, not reach your target, and it's probably going to land somewhere where you don't want it to, somewhere which is unsafe because of how far it's gone from your launch site. Which is why centering rings are so important. Okay, so that's most of the rocket done, but there is actually one last topic, and that is the fins. For this rocket, unlike our past rockets, we're going to be using carbon fiber. And that's because it's light. You may see it used in F1 cars, and that's because of how strong it is for the weight it is at. It's much better than using aluminium or wood, because aluminium is much heavier, and wood is just not strong enough. You're going to have to make it thicker, and the thicker you make it, the more drag you have on your fins. It's less aerodynamic, which is not what you want on your rocket. You need to be as aerodynamic as possible. So we're using carbon fiber fins because they're thin, and they're very, very strong. But they also have some downsides. Carbon fiber is expensive. It is really expensive to get carbon fiber, but it's okay because when you're using them for fins, you can buy little sheets that you can just cut yourself and make yourself. which is considerably cheaper than buying them off a carbon fibre cutting company, which normally specialise in making quite detailed things which need expertise. Things you can just do them yourself and cut them yourself with a Dremel. So that's the end of this video, and I will talk more about the electronics and more about the recovery, because in this video I was trying to give a brief explanation of the entire first version of the rocket. So I will start to go more into details on specific areas of the rocket after this. So that's the end of this video. Thank you for watching, and I would just like to ask that you subscribe, because this project is run by students and there's not that many of us. So by you subscribing, it's completely free and it helps out quite a lot. Thank you.